Hi there. So I am going to do the best I can to kind of explain a little bit on what simple harmonic motion is. And how this is going to go is I have a couple videos installed in this quick little tutorial. And after I show the videos, I'm going to talk and lecture just a little bit to help you kind of understand what's happening here. So we're going to start with Professor Dave.
Professor Dave here. Let's discuss simple harmonic motion.
He knows a lot about the science stuff. Professor Dave explains.
Sometimes when we examine the motion of an object, it will involve a single action, like a rock falling from a cliff down to the ground. This will probably just happen one time, after which the rock will remain at rest. But some motion is periodic, meaning repeated, like the motion of the pendulum on a grandfather clock, or the vibration of a spring. We will refer to this kind of motion as simple harmonic motion. Say we have a spring that is attached to some stationary surface, and on the other end of the spring there is a block of a particular mass. If we pull this block so as to expand the spring, and then we release the block, it will vibrate back and forth between more compressed and less compressed states. If we assume that the surface of motion is completely frictionless, then the elastic potential energy reaches a maximum when the spring is most or least compressed and the block is changing direction, while kinetic energy is at a maximum when the block is right in the middle and moving the fastest. If we were to graph the position of the block against time, it would display sinusoidal behavior, just like a trigonometric sine function, where the block continues to occupy the same positions over a particular period of time, which is why we call this periodic motion. X equals 0 at the equilibrium position of the block, where it sat before we pulled it, and assuming zero friction, the block will oscillate between positive x and negative x indefinitely. In reality, frictional forces will dampen the spring's activity, and it will eventually come to a stop. But for many systems, an ideal mass spring system will be a decent approximation for a real one. Of course, every spring is different. Some are loose, like a slinky, and some are stiff, like the spring that launches a pinball into play. This factor is represented by the spring constant K, which will be unique to a particular spring. The force that a spring can exert is equal to negative K times the displacement of the object it acts upon, and this relationship is called Hooke's law. The negative sign indicates that the force of the spring is always opposite the direction of the movement of the object. When the object compresses the spring, it will push out, and when the object stretches the spring, it will pull in. In both cases, the spring is attempting to move the object back to its equilibrium position, which is why the force applied by the spring can be called a restoring force. The units on a spring constant will be newtons per meter, so that when you multiply by some distance x, you get the force that must be applied to compress that spring that far. Let's also note that the elastic potential energy of a spring will be equal to 1/2 kx squared, where k is the spring constant and x is the distance it is stretched or compressed. If at equilibrium, the distance is 0, so it has 0 elastic potential energy, and the maximum elastic potential energy will occur at the maximum distance from this point on either side of the oscillation. This expression looks similar to the expression for kinetic energy, which is convenient since the two will interchange as the mass oscillates. A pendulum also displays periodic motion since it swings back and forth between the same two positions. Although this involves gravitational potential energy rather than elastic potential energy, and we will look at this behavior next. Let's check comprehension. Professor Dave.
Sorry about that.
Professor Dave.
So I wanted to show that to you because it did some kind of motion in there that I just don't have time right now to produce. So I thought that was kind of nice. So overall, what we're talking about here is simple harmonic motion. And there are lots of examples of this. They gave you the idea that this pendulum, if you see an old clock or something going back and forth, if you're looking at a little kid playing on a playground and they're basically moving back and forth on a swing, that's an example. Car shock absorbers, when you go over and it's going back and forth and it's kind of bouncing the car. Musical instruments, as you sit there and hit, say, a guitar, and when the strings vibrates back and forth, even all the way to something that I love to teach so much is about hearing and how essentially the tympanic membrane in your ear oscillates back and forth whenever it's hit by molecules that are kind of oscillating back and forth from something that has been hit. And so that's how sound moves. All of these are examples of simple harmonic motion. And so, as it said, it's about something being periodic. And periodic motion is just something that's saying that it's repeated. So if I periodically go check my cell phone to see if I've gotten a text from my son, it says that I'm going through in these repeated intervals to go check my phone. So that's what it means by periodic. And so you can look and say, is this motion happening over and over in this repeated idea in equal amounts of time? And so we need to understand this. We need to see this happening in order for us to understand harmonic motion. Now, within this, essentially, if we're looking at things moving in this repeated pattern in equal intervals of time, basically, if we see this happening over and over and over again, essentially we can take that repeated movement, and that is what's known as an oscillation. And so basically, let's look at what an oscillation is. And so say I have this wire here, and when I don't touch it, it goes straight up like that. But then you can see I have this finger and I basically move it this way. And so it starts moving back and forth, going this way away from that position that we start is called the equilibrium position. So every time, don't get confused by these terms or definitions. They're just talking about these moments and giving them a term so that when we talk about these events occurring, we all know, well, what's the position that it started in? Well, that's what's known as equilibrium position. And this just, if you look, it means equal or no changes happening. And so that's what that is right there. And so essentially, we have these terms called periods. And remember, we were talking about periodic motion. So this is how many times can this oscillation or this movement happen? And so we look at that in terms of seconds per cycle. And then the frequency, so this is, a period is the amount of time it takes for one of these cycles to happen. And the frequency is looking at how many of these back and forth or oscillations do we get in a certain time. So when we're looking at that, we're just talking about how many cycles are we getting per second. So period, how long does it take for this to go back and forth? Once. Frequency, if we have a second, how many times can that happen? And so let's do a really quick example here so that we can kind of get an idea of what I'm talking about here. or trying to compute what this period is. So I have two baseball players that warm up with a game of catch. If it basically takes 6.6 seconds for the ball to go from one player to the other player and then back again, what is the frequency of the ball's motion? So essentially, if we're talking about here, we said frequency was, which stands for F, how many cycles, which we're just looking at, if we're looking at one cycle, the number of cycles per unit time. So here we're looking at just one cycle, right? So we know that it's given here by basically the number of cycles versus how much time. So in this, we're trying to find the frequency. We know how many cycles we have, and we know how much time we have, which is 6.6 seconds. Then essentially what we can do is take 1 divided by 6, and we get 0.15 hertz. Again, if you remember, we have two sig figs here, right? Which is why, if you look, we have two sig figs here, and this is just considered a standard, so we don't use that. So this is how you can calculate frequency. Now, we're still not getting to actually we're looking at parts of simple harmonic motion, which we use or shorthand it for SHM. So simple harmonic motion is basically when an object moves to and from along a line. The motion is called simple harmonic. So we were just looking at that in terms of, oops, I am so sorry about that. I don't know what happened there. So when we're looking at this, right? So if we're looking at this moving back and forth, back and forth, back and forth, that can be an idea of simple harmonic. So you've seen a pendulum. Basically, you can start it here, right? And then it can basically move back and forth. When we swing it, it moves to and fro along the same line. These are called essentially oscillations. So that's what we were looking at in the last one. So you had a lab, and you've had some of these looking at these ideas of what we're talking about. So let's look at an example here. So essentially we have this spring that's positioned, and one part of it has a fixed end here. And then on the other part of this, we have this weight. And then essentially what can happen here is we can take this spring and we can either push it this way using the weight, or we can pull it this way. Right? So this right here that we have, and if we look at it and say this is a line, this is what we have where this spring is at its natural length. As in, we're not trying to straighten it out and we're not trying to scrunch it up. This is where that spring naturally lays. So this is what's considered the equilibrium position. There's no force on it, nothing's happening. Now, if we take this and we decide to basically go from this position and we give it basically a push in. We're displacing it from equilibrium, which means we're moving it from its origin. So this movement here, from here to here, is what's known as x. And if you look, they say that's what's known as a displacement from equilibrium, or just in layman's terms, how did we change it from the original position? Now, if we take this and we push it in, this spring has kind of what's known as some kind of resistance to it. As in, you've taken some slinkies before, if you've ever played with them, and you pull them out and they're really easy. Or maybe you've seen the coils in a mattress and you've tried to push on them. That's a lot different how tough that is, or how rigid the springs into a mattress, versus if you pull out a spring from a pen that helps to basically, when you push the pen down, and helps the writing portion click out, and then you push it back in to release it up. If you take a pen apart, you'll have these little springs in them. And so each one of them has a different amount of rigidness to it, or resistance to it. That resistance the spring has, or how rigid it is what's known as K. Now, if you look in your handout, K says a constant of proportionality, which you're like, what in the heck does that even mean? And so in layman's term, it's just saying, well, how resistant is the spring to being pulled or pushed? And so we have this formula that we have that's called f of x equals negative kx. This is known as Hooke's law. That says we can figure out how much force it takes to get this guy here back to its original point if we push it or pull it. Right? So let's look at this really quick. So, if we have basically, this is the original x, and we push it in, then essentially what we have, this is this guy that's right there. If we look at how much this guy fights the change, right? How rigid he is. That is this guy right here. Now let's talk about this. You know how springs work. If I push this guy in, if I push it here, he's not going to stay there, right? You push a spring in, it bounces back. So basically, the amount of force being basically demonstrated here to get this guy back to the original position. That's this. And what I want you to notice, which all of a sudden makes so much more sense here, do you see how this is negative? Well, that's because, do you see how this guy right here, oops, sorry, this right here is going this way. This right here is going this way. So they're opposite, which is why that guy is negative. So essentially at any time, if you have two of these bits of information, you can find the third. Now, these are the units that you'll generally see here. If you look down here, you have newtons for force here. You have meters for how much is it going to move. And then you have newtons per meter, because this is going to tell you how much force per meter it's kind of resistant. So I like to think about this in terms of little kids, right? If I have a little kid and I push them one way, that little kid, you know, they're ornery. They're going to push back on you. They're going to if you're like trying to move them to the spot that you want them to move, then they have their own amount of force that they're going to push back against you so that they can get back to the initial spot. And so that's how this works. This essentially, if you look at it, this is how much you've moved them. This is how ornery they are, or how much force they're going to pit back to you, right? Or how much natural spunk they have. And then this is going to tell you how much force they're pushing back to you to get back to the initial place they were. So how much you moved them, how ornery they are, and how much resistance they're giving you, and then how much force they're exhibiting to get back to the initial spot. And so that's what we can look at in just basic terminology here, right? So let's watch this really quick so you can kind of see a next step. And then we're going to talk a little bit more, because if you look at some of the handouts, they get into a little bit of trig. You do not need to understand the trig to do it. You're just going to, if you kind of understand where it's coming from, then you just plug numbers in.
Today we're going to talk about,
So we're going to get to
some
here.
Springs ranging from rather weak springs to some tough, strong springs that are tough to compress or to stretch. Hooke's law governs the force of the spring on your hand when you extend or compress the spring. If you extend the spring by a distance x and multiply that extension by the spring constant, that gives the force. And the force that this spring exerts on your hands is always opposite to the displacement, this amount of stretch, x. So let's show, for example, for this spring, its equilibrium length is about 12 centimeters, as you can see here. If I stretch it out to a length of 17 centimeters, then in this case, x will be 5 centimeters, from 12 out to 17. But the force that the spring exerts on my hand is opposite the direction that I displaced it. I displaced it out this way, and it's pulling me back toward equilibrium. The same thing happens if you compress the spring. So if I compress the spring now down to a length of about 7 centimeters, then the spring pushes back on me. It tries to get back into equilibrium again. That's Hooke's law. Okay, just the force exerted by a spring on your hand when you stretch or compress it is given by a negative sign, and that tells you that the spring is that the force is in the direction opposite the displacement. If you pull the string, it tries to pull back on you, etc. K is a spring constant, has units of newtons per meter. That's because the displacement x always is in meters, and if the spring constant is in newtons per meter, then you have newtons per meter times meters gives you newtons for a force. And so just noting here in this figure that if the displacement is to the right, the force is to the left. That's this minus sign, its work. If the and this is a positive displacement, that displacement to the right, x will be a positive number, and f of x will therefore be a negative number. Or, if you compress the spring, then x will be to the left, will be negative, and the force will be to the right, because you've got a negative sign here and a negative x, and that'll give you a force that's in the plus x direction. Noting here that x is positive, measured positive toward the right. You have to measure it from the unstrained length.
So what we're talking about here, essentially, or what he was talking about, let me get on here. And so here is a spring, what we've already looked at, right? And so if you see this, this is saying that the equilibrium is at 0. So at this point, this spring is happy, if it could be happy, right? And so there's no movement. It's in its natural state at the initial equilibrium state. So essentially, the force is 0 because there's no displacement of x. But say, for instance, here, do you see we started here and we stretched it out? So say if this was 10 and we 10 meters, and then we stretched it to 15, right? Essentially, you would have your final is 15 meters minus your initial, which is 10 meters. So that would equal 5 meters. So this essentially is positive. That's why he said it was positive, because your number at the end is larger than what you started with. Now, all of these, the K is constant here, because this is the same spring, right? It has basically, we're looking at how sturdy is that spring. So that is going to be given to you, essentially. You could calculate what the spring constant is. Remember, if you have the equation, which is F of X, this X is just talking about how much of your change you're seeing, right? Minus KX. So if you're given the force and you're given how much it's moved, you can figure out the constant or the displacement constant there for the spring, or how sturdy it is, or how much, essentially I like to think how resistant it is to forces. But if you look, if you've moved this way on here, then essentially the force that is trying to get it back to here, which is known as, this is the restorative force, right? Or restoring force, because it's trying to restore it back to the beginning. It's moving this way, right? So that's why this one is negative. Now, if you go and you compress, you can say we started here and say that's 10 meters, and maybe now we've compressed it this way, and so essentially you have it at 5 meters. Then essentially what you're doing here is X equals your final, which is 5 meters, minus 10 meters, which equals negative 5 meters. So that's why X is less than 0. And so this guy is going to be negative. So when you start looking at the force, right, when you're looking at this displacement, you're going this way. When you're looking at what way is this guy going to push to try to get it back to normal, he's going this way. So that's why it's positive. So that's the basic algebra of Hooke's law. But what we're not considering here, we're taking snapshots. We're being static right now. But that's not how this would be. If I went and did this right here, and I pulled it this way, this guy is going to bounce back this way, and then go this way, and go this way, and go back and forth, right? And if there's nothing that's stopping it, as in something like friction, it would just move back and forth constantly. Now, if there's things that are opposing the movement, then it will slowly stop and go back to here. But if there's nothing, it will keep moving back and forth. And so, do you see? If I were to push this up, it's going to go up, and then it's going to bounce down and do this, right? And then it's going to move, and then it's going to go down. Do you see how this is moving up and down? Well, depending on this kind of wave function, that is what's known as a sine or cosine function. And basically, when we're looking at this, let's think about some of the things we've talked about so far. Remember how we were talking about period? How many times you get this oscillation happening within, a certain amount of time. So if we get one oscillation, this is a period. Now, how big this oscillation is, whether it's to this trough or to a peak, that's the amplitude. And here, they're talking about a period being from the top to the top. It's almost like one wavelength, right? And that a cycle is in red here. And so, depending on how this moves up and down, you can either have it if it starts here. All this is saying is if you have a sine function, it starts and moves up and down like this. If you have a cosine function, it stops and moves up and down like this. So basically, this is just showing you how much it would move down and then come back up as you pull on that string. You don't have to understand in this class. It's not about understanding how do we get to this math. That's trig. That is a whole step past this course. You don't have to understand the function itself. You just have to understand that that spring is moving up and down in these cycles. And just depending on how it looks, depends on if it's sine or cosine. And you essentially can use the math and plug stuff in to determine things like how much has it moved in time? Or how fast is it moving back and forth at a certain time? Or how much speed is it gaining at a certain time? So when we're looking at this guy, right, and he's moving up and down, this guy, remember when we looked at T, 1 over F? What was this? What does T, 1 over F stand for? Basically, we're saying how much time does it take for one cycle, right here, right? Time equals 1 over F, which is frequency. So this, you can rearrange it. Essentially, frequency equals 1 over T. So if you want to see basically the idea, right, the time, how much it requires for one cycle to go through, this would be a period. A is the amplitude, or how much change you're seeing, right? And then essentially here is talking about things like angular displacement. So what we're going to do with this is just take this out and let's talk a little bit about what you can do from this. So if we want to essentially look at how much change or displacement, right, this guy from its original equilibrium position, we can go change or displacement at a certain time. So we can look, for instance, here. At that time, do you see how we're in, as we go this way, we're looking at different times. Basically, we can figure that out by using what's known as a cosine of 2 pi t over big T, which equals a cosine of 2 pi ft. So what does that mean? This is the amplitude. So how much of this change do we see? How big was that movement? This little t here is the time. This is in seconds. The amplitude is in meters. So essentially, when we're looking at this, what's the snapshot? What's that moment that we're trying to find? The displacement. Big T is the period. And you can see that's from here to here. So somewhere in this time, right, we're taking a snapshot or a point of that. Frequency. What is frequency again? Frequency is just looking at how many cycles per second, right? So 1 over the big T. So if you look, all we've done here is, do you see how this is 1 over big T? So what they've done here, this is the same equation. They've just taken the 1 over T that's here, because there's 1 on top, and put it in here. So if you have this different information, you can easily find how much displacement is happening at this point. Now you can also look at not just that. I'll give you a second to write this down and then we'll move to the next point. So we can also look at velocity, or how much change at a certain time. Oops. Sorry. And so all that's saying is you have a certain let me write this down. I'm sorry. No. I went too far over, so let me do this again. And I'll go as I go through. So this is just saying this Vx over t is saying what is the velocity at a certain time. So how fast is this guy moving here? Right? And then remember we said the sine and cosines are just these different wave functions. And so all that they've done here is like what we were doing a minute ago. You have Vmax is what is basically the maximum velocity. And this guy is basically the maximum velocity is 2 pi fa, which is basically 2 times pi looking at the frequency, right? Which is how many cycles per a certain or a cycle per second. And how big or how much amplitude or change do you have here? And so that's the same as 2 pi at. Because if you remember, what all they've done here is taken this f here, because if you remember, f equals 1 over t, and put that here. And so you can find out what the max velocity is happening, or what is the velocity at a certain time point, or how fast it is, by plugging in this information. And the last part of this is you can do the same using acceleration, or how much speed is being gained. And so you have a of x over t. So how much speed or acceleration is happening at a certain time? And it's the same idea. You just look at this is the acceleration at a very specific time. You can find this in meters per second squared. And this, they can tell you what's the maximum acceleration that's happening in this period, right? And then from there, you can find out the information by just plugging and playing. And of course, as we always know, that f can equal 1 over t, so you can put this in, you can put f in for 1 over t. And so all of these are just kind of examples of how you can find different information based on these parameters, because this little guy here is just moving up and down in these very periodic motions that follow these sinusoidal functions. So essentially what you can do, we can do one quick problem here, and it says that we have an air track cart is attached to a spring, completes one oscillation every 2.4 seconds. At t equals 0, the cart is released from rest at a distance of 0.10 meters from its equilibrium position. What is the position of the cart at? So what is the position of the cart at 0.03 seconds? And so what we can use here is the equation x equals a cosine of 2 pi big T over little t. And so essentially what we had is, if we look, let's draw this guy out, we have the initial equilibrium, right? And so essentially when we release it, it can be one of two ways here. You can have the x going back and being 0.1 meter, or x being 0.1 negative meter. So it's going back and forth like that, right? It's displacing back and forth. And so essentially what we're going to do is, in here, it's not essentially, in our sketch here, we place the origin of the x-axis at the equilibrium position here of the cart, and we choose the positive direction to point to the position or to the right. And the car is released from rest at basically what they said, 0.10 meters, which means that it's the amplitude, right? Because we're saying how far, if this is the position, how far is it basically being displaced? So that's our amplitude. And after we release it, that car is going to oscillate back and forth between that 0.10 meters and the negative 0.01 meters. So I want you guys to notice that the period of oscillation here, right? That's the period of oscillation. So that's the big T. So we're going to start putting boxes around stuff so we can see. So that's our period of oscillation. This is our amplitude, right? So then we can find the position of the cart by evaluating this equation. So essentially we have 0.10 meter, which is our amplitude, times cosine of essentially 2 pi, and the big T is 2.4 seconds. That's our oscillation, right? Times, we're trying to find it at what time? The little time, which is 0.30 seconds. And so essentially what happens from here is you go 0.01 meters times cosine And then essentially what we'll have here is pi over 2 actually pi over 4. Sorry, I'm calculating things out right now. Which equal 7.1. We're going to go into centimeters. We change from meters to centimeters because of the way to write your scientific notation, real notation. And so this kind of explains, hopefully, a little bit on what's happening with this stuff. And if you need any more help, just please let me know.